news articles of interest. The first one is the one this student just told me about. We all know that SolarWinds had a supply chain attack where the attacker was able to add malware to their machine, to their software, which then infected many companies. But this guy seems to have done the same thing through open source projects, infecting 35 companies. Alex Bursan, he was able to add malware to Ruby Gems, PyPy, and NPM, which is pretty much using software that everybody uses. And so he was able to take over Apple, Microsoft, PayPal, Netflix, Yelp. That's amazing. And all he had to do was make counterfeit projects using the same name, and applications would automatically pull the package without needing any action from the developer. So this sounds like a really serious flaw. I'm very surprised that you can even do that. That's very wrong. I mean, if you apt-get something or pull something to include it in your Python library, there should only be one package with each name. But he found, anyway, that's very interesting. So he got $40,000 of bug bounty, and we certainly need to fix that. Anyway, a very interesting article. This is very appropriate for the CISSP. This is about how to get along with management. So these are the side of things. I don't think it's in the CISSP exam, but it's the right kind of content that should be. This is, in fact, in the content saying that the purpose of security is to further the company doing the mission of the company. Security itself is not the point. Security is just part of, security people have to understand that they are there to facilitate the success of the company. And it's not that the company is there to facilitate security. They tend to get this arrogant attitude that security is what's more important than the other business decisions, and that is the way to fail. And in various ways, that information is, in fact, on the CISSP exam. And, other business things like learning how to communicate effectively without being too pushy, and how to build relationships. These are all very important issues. And they talk about the importance of moving around. Having both a technical job and a management job would make you stronger. Anyway, these are very good career tips, and I think a lot of my students in the management classes are oriented towards that. And I mentioned this in my other classes. This is an example of a disaster from white hatting. This guy found a product called Footfall Cam, discovered that it was appallingly insecure, incredibly amateurishly made, and he revealed it, and then the company offered to hire him to be a consultant to help fix it. And when he sent them a proposal, they accused him of trying to blackmail him and made a bunch of fake accounts, accused him of being racist, reported him to the police, and just tried to make all sorts of trouble over it, which tends to happen. That's why, it's the general path of safety is to not do any security research except on companies that have contracted you or that have posted a bug bounty proposal, so that you know that there is somebody at the other end who is interested in hearing a vulnerability report and will have some idea what to do with it. If you just throw a vulnerability report at a normal company that they're not expecting, they tend to freak out. And I thought this one was good for the management class also in the same spirit. I mean, this guy was told by his hospital, he's a doctor, that whatever you do, never waste any vaccine. So if somehow you have some vaccine and it's going to expire, just give it to anybody. So that happened late at night. He had a vial of vaccine with some doses left. So he went home and called everybody he knew to send over any sick relatives or anything and vaccinated people. And then they called him in and said, the problem is all the people you vaccinated had Indian names because his circle of friends had Indian names. And therefore that's bigotry, and therefore you're fired. And we're going to tell everybody that you stole the vaccine to vaccinate your friends. And now he's blacklisted and lost his job, and everybody hates him and they're threatening him, and he's been turned into a monster. And so we'll see what comes of this. I would think there will be some lawsuits and such, but this is a very similar issue as those people that report a vulnerability and end up in huge hot water over the political issues. And, a lot of these struck me as particularly relevant. And here's another thing. Security people like to say that you should secure all your stuff, but in fact, there are parts of your company, and there are companies that don't know much about security. So these water plant people just used the same TeamViewer password for everything, and everybody knew it. and SolarWinds that led to that huge supply chain breach. SolarWinds just used the password SolarWinds123 as the master password for their remote access solutions. So after that breach, various other people said, hell, everybody could get into SolarWinds servers. I used to go there years ago. Their password policy is pathetic. So it's very often the case that people have very, very poor security, and it goes on for a long time. Anyway, we're up to the official time. So here we are in 125. And what we're going to do today is the first of three lectures on security engineering. And a student pointed out to me it wasn't clear what pages are covered, so I added that here up to the topics. I don't have page numbers in my online book, but I have the topic numbers. So I'm just checking for questions, and there aren't any, so I'm going to go here, and we'll do the first three sections of this. All right. And there, it looks pretty good. All right. So we're going to go through security models and evaluation methods, and down to some things about hardware, operating system architecture, and virtualization. All right. So security models, this is the stuff that I found unique to the CISSP and really quite interesting. This is the history of the sort of mathematics and computer science underlying the concept of security, which is what led to all the devices we're using, and also to the military and business models of how you measure how secure something is. So the basic concepts are up and down. Down is unclassified stuff, up is more classified stuff, and so you have levels which do not need to have this name, but they typically do have this name in the military: unclassified, confidential, secret, and top secret. So when you talk about up, that's up to a level of higher secrecy, and down is to a level of lower secrecy. And of course the issue is then whether you can read up or read down, and so on. So the simple security property, when people first started trying to invent the idea of what security is, they thought, well, security, the only thing they thought about was confidentiality. They said security means that nobody can read the secrets unless they're authorized. So there's no read up. You can't read anything that's at a higher level than you are. So if you're only cleared to secret, you can't read the top secret, and so on. That is the simple security policy. And they formalized this in the world of mathematics and computer hardware is the Bell-Lapadula model. That is the mathematical model that implements this feature. And it turns out that that is not as wonderful as people thought it would be. You figure that's it, now you've got security, but it's not that simple, because you can't read up, but you can write up. For example, you could discover something at a low level, which is then classified and moves up. That doesn't violate confidentiality. Now, there can be no write down, because you don't want people taking top secret data and writing it down to a lower level. That would only happen if you actually go through some kind of declassification process so that it is no longer top secret. So that would violate confidentiality. So you have no read up and no write down. Those are the rules. Now, read down is okay, of course. People with top secret can read secret or lower classification. That's fine. So out of the four possible operations, read up and down and write up and down, you allow two and you forbid two. That's the model of Bell-Lapadula. Now there's a state machine. These things are all called state machines. That's the mathematical structure of them. You have a system, you have files and users and things, and that's just a group of objects in some state, and everything that happens is moving from one state to another state. So you want to define which states obey your security policy and which ones violate the security policy, and then you want to make sure that you only allow interactions that maintain the security policy. That's the idea. So this is the Bell-Lapadula model developed for the Department of Defense, and those are the two rules: no read up and no write down. Those are the two rules which lead to this system, and this protects confidentiality. The problem is it does not maintain integrity. A low clearance operative could submit false data which moves up to high clearance levels, and nothing prevents that. In fact, a low clearance model could modify high level data, and that is not prevented. So this maintains confidentiality, but it does not maintain integrity. And this is, I think, how they developed with the concept of confidentiality, integrity, and availability as the three security properties they started with just confidentiality and then discovered that that doesn't really work so well because it doesn't maintain integrity. All right, so tranquility is the property where your security labels don't change, and weak tranquility property is where security labels don't change in a way that violates your security policy. So there's lattice-based access control, and this is another possible model where you have subjects and objects, the people and the files and folders and computers they might want to get to, and these have various classifications, and subjects have a least upper bound and a greatest lower bound of access. So they have levels written as things like alpha, beta, gamma. That's the highest level of access. So it's a strange sort of two-dimensional model with things like this. These guys have no privileges. There's alpha, beta, and gamma groups. This guy can do alpha and beta, and the person who can do alpha, beta, and gamma has the highest privileges. That's the idea of this one, and I don't really understand exactly how it works. But especially for the CISSP, all you're really trying to do is recognize like the top 2 or 3 facts about each model. And the ones that really matter most that are the BIBA, the Bell, and the Clark-Wilson. Those are the 3 which represent the steps forward in really understanding security, and the rest of these are the minor ones in between. So the BIBA was the one to fix the problem with the Bell model. The Bell Lapadula model did not maintain integrity. It only maintained confidentiality. Now the BIBA model just does the opposite. No read down and no write up. So you can't, if you're at a top secret level, you can't read non-top secret stuff. This way you don't learn false data at a low level, which corrupts your knowledge of what's going on at a high level. And no write up means low-level data cannot move up to the high level. So you keep it pure. And when I think about this is essentially, I think, what the Catholic Church is. You have this thing at the top called the Bible. Nobody can ever change it, and nobody ever reads. The people at the top go directly to that and trust that. And the idea here is you maintain integrity. Your high document is maintained completely unaltered by this system. But it has no confidentiality. Everybody can read right up to the top level. So you have, this is more what you might want in businesses or in a church, where you have this, like in the Catholic Church, you got this holy book and everybody can read it. It's not a secret at all. There's never any secrecy, and that's supposed to be the highest authority, so everybody can see it all the time. So it doesn't have any confidentiality, but it has integrity. Now, in reality, for a business or the military, you need to have some balance of integrity and confidentiality, so neither of these models alone is right. They're both too extreme. So the Clark-Wilson is the one which we are actually using, closer to the one we're actually using, where you have some kind of mix of the two. So you have your subjects access objects, and you have 2 concepts, well-formed transactions and separation of duties. So well-formed transactions work like this. You have data items that come in, like untrusted user input. Then you have constrained data items. Then you have a transaction procedure which maintains integrity and can convert an unconstrained data item into a constrained data item. So you have data coming in you don't know about. Then you pass it through this transaction procedure to put it into data that obeys your security model. Now it's properly labeled and categorized and put in some place, and there's an audit record. And then people do things, and you have separation of duties, so 2 people have to agree for high-value transactions, and you limit the transactions, again, to the ones that maintain your security policy. And now you can have a realistic security policy, like, say, a Microsoft Windows domain controller, where it's not as extreme as no read up or no write down. You have groups of people like sales and development and management, and they have certain things they can do and certain things they can't do in a more complicated array, so that you maintain the correct mixture of confidentiality and integrity. All right, so let's take a look at 3A cahoots, which are up here. And this is sheet at 125. 3, is that an A? I think that's an A. It's an A, all right, good. 26 people in the Twitch, so I think we'll probably have a few more here. I guess that's it. Nope, I guess not. All right, I'll wait a few more seconds. All right. So which model has confidentiality but not integrity? It's the Bell model, and by the way I remember this is they are in alphabetical order. Bell, Biba, Clark Wilson, and they're in the logical order of development. First you worried about confidentiality, then integrity, and then you mixed the two. Anyway, all right. All right, which one uses alpha, beta, gamma? Okay, that's lattice. Good. Which one has no read up? Okay, that is Bell. The same, no read up means the low level can't read the high level. That's confidentiality. All right, and which one has no read down? That's Biba. The people at high levels do not read low-level things. All right. Roman. Sounds like might be a real name. That's also looking like a real name. In fact, I think I remember it's short. And this one. All right. I know who that is. All right. So. Checking for the comments, and there aren't any, so we will proceed. All right, and so then we got a few more models. There's an information flow model that limits how these things flow, and that's the type of model that includes Bell, Lapadula, and Biba, where you limit how information moves with things like no write up and no read down. There's a Chinese wall model, which is what I've seen it in legal dramas on TV, where you have a company that represents two different activities that have a conflict of interest. So you define an internal wall where only certain parts of staff will work on this case and the rest of the staff will work on that case, and they're not allowed to talk about it. So you can avoid having a conflict of interest with internal walls inside a company. Non-interference. Is that no longer PC? Well, I don't know about that. As far as I know, this still happens. I haven't heard about any law coming out against this or anything. And a non-interference is a desirable property of any security system. And this is something you would like to have, which means that data at one level will not affect data at another level. So things that happen at the unclassified level will not affect anything that happens at the top secret level. And this is another reason why in the military they like air gaps. You'll have a separate computer for top secret and classified and unclassified, and they will not be connected to networks, and there'll just be completely different hardware running them. Now that's probably the best way to achieve non-interference. It turns out to be very difficult to really achieve this in practice. It turns out if this fails, then there is a covert channel, and you can measure something at one security level that tells you information about another security level. And one example of that is you can identify a cryptographic key by measuring the power consumption as the processor uses it. So measuring something that's not secret lets you determine something that is secret. And there are a lot of examples of that. Take grant is another model where you have these kind of rules. You can grant permission to someone to do something. You can take the permission away. You can create something and you can remove something. And now you have a model of who's allowed to do these things. And you have a complex graph of relationships. So Alice can create and remove permissions to the secrets, and she can give Carol permission to access them, but Bob can take away Alice's privileges. So you rate people by what powers they have on the system. And so you'll have a matrix, read, write, and execute, who's allowed to do what. This is an example of an access control matrix that you might see in Linux or Windows in a sort of simplified manner. And then there's the Graham-Denning model, where you have subjects, objects, and rules. And you see these are the kind of things you might want to do, like read something, or destroy something, or create something. And there are rules of which of these powers each person has. Then there's the HRU model that treats subjects and objects the same, but only has 6 rules which apply to both subjects and objects. These are all just different ways to lay out the permissions, and they have different mathematical consequences. All right, then you got modes of operation, and this is determining the level. This is from a DoD directive, so there are 4 modes of operation for a secure system. And here's how it works. The first one is the one I just described. The most secure model is the dedicated model. You just have completely separate objects for all the different classification levels. So the only thing on the secret computer is the secret stuff. And the only people that are allowed to use that computer are people who are cleared for secret or higher and have access approval and need to know. So that's where you have dedicated devices. Then there's system high, where you put objects of mixed labels on the same device, but if it has data up to top secret, the only people that can touch it have to be cleared to top secret. So you do have some mixing of levels, but you never have a low privilege subject using a machine that has any high privilege data on it. Then there's compartmented. Another way to do it, everybody has to have the necessary clearance, but they don't necessarily all have the formal access approval. They're placed into compartments, and you have technical controls to limit that. So something about your login will say, I am cleared. I have a top secret computer, and I'm one of the top secret people, so I can log in, but when I log in, it will then decide what my need to know is. And there is information on that machine outside my need to know, but something about the operating system is blocking it by recognizing my username and not letting me see it. And then the cheapest, most common system is multi-level, where you have everything all mixed on the same machine. The objects have different sensitivity labels, the people have different clearances, and you have some kind of software running on the machine called the reference monitor, which limits what you're allowed to do. So even though there's top secret information on there, if I log in and I'm only cleared to secret, the system will recognize who I am and have controls so I can't get at the top secret information. There is not an air gap protecting me. It is this reference monitor software that is protecting the data from me. All right, so if you're going to consider these different ways to do it, you want to rate how good they are, and so there are evaluation methods to determine whether you are good enough. And the original one was the Orange Book, the TC-SEC. This was developed in the 1980s, and it was going to define what you have to have of a computer system for it to be secure enough. There was a series of these things called the Rainbow Series of military specifications, part of NIST. So it rates your security from A to D. A is the best, D is the worst. So D means your system has essentially no security at all. C is discretionary protection. This is like your home computer. You have your computer, you can put anything you want on it, you can let anybody else use it, you can make an account and let other people use it, you can deny people. It's at your discretion. It's owned by an owner, and the owner can do anything they want. Mandatory protection is where the owner doesn't have the right to make those decisions. They have to ask some kind of boss. Is it okay if I let this other person in there? So there's the typical military model where you have to get something classified by a higher level, and you have to, if you want to declassify it, you have to submit it to some person above you who will then decide whether it's okay to declassify it. There is a process for this. And the highest level is verified protection, where not only is access controlled and enforced by authority above you, but it is also managed and audited to make sure that it stays up to date and document, it's this is verified, where the best level of protection is there, and there is a process of supervising it and making sure it stays that way. That's basically what these levels are. And of course, you're going from the cheapest system to the most expensive system. Up here, you've got a whole bunch of managers and supervisors and paperwork flying around to get everything done, and a lot of delays. And it's going to be a lot more expensive to achieve this. But if you do, then you can actually work on classified projects and such. So there was the Red Book, which made a similar thing for network systems. And then there was the European version of it called ITsec, which tried to accomplish the same thing using different languages. So it had a functionality and assurance. The functionality is just how well the system does its job. And then you have effectiveness and correctness as parts of assurance. And so you can have assurance correctness from inadequate to all the way up to E6, which is the formal model of a security policy. And their functionality ratings are comparable to the Orange Book equivalents. You can compare the two. So here's the Orange Book levels from D up to A, and here's the European system with just different levels amounting to essentially the same thing. And both of these have been superseded by common criteria. In about 2005 or so, they combined them and made the new system, which is intended to replace them both and be common across the United States and Europe. So you have the target of evaluation, the system you're evaluating, and you have a security target defining your goals, what you're trying to achieve, a protection profile, and an evaluation assurance level, which is the score it gets. And here are the evaluation security levels. They go from 1 to 7. 1 is functionally tested. It just does its job. 2 is structurally tested. There have been some tests to see that there is some security controls. Then you have methodical testing and semi-formally testing and verifying, and the highest level where there is a formal process of testing it, designing it, and verifying it. And again, the same blizzard of administrators and papers flying around testing it and proving that it's been tested and documenting that and everything else. So that's the modern system to accomplish the same goal. All right. So we got another Kahoot. 3B 125. It looks like the right one. All right. All right, looks like we got everybody up. Maybe not. All right. Okay, what feature prevents a covert channel? Okay, that's non-interference. All right, what mode enforces an air gap between each level? All right, that's dedicated. You have dedicated hardware for each level. All right. All right, what mode uses a reference monitor? It's got a 30-second delay, Levon. I mean, it's giving you 30 seconds for each question. And the delay I checked is 3 seconds, so it's... right. You should be able to answer question 3. Are other people unable to answer? You should have like 27 seconds to answer. It might be that you're going to lose the last 3 seconds, I think, because of the lag, but that should be all. I see the buttons to select about 10 seconds before the question. Then maybe the lag has gotten too long. I found a solution last time. Let me stop streaming and restart the streaming. Let me try this again. First, let me check it. 1, 2, 3, 4, 5. All right, it's 5 seconds. I'm going to stop streaming and restart it. Well, could not access. Okay, let me try it now. All right. Now let me test it. 1, 2, 3. It's better. It's back up to 3. Okay. Good. Thank you for letting me know that you have trouble. I think this has fixed it. We'll see. But there's always something with these streaming things. So let's try another question here. I think there's another one coming. And see if it's better. All right. How about a home laptop? What Orange Book level is that? All right, that's C. I would have thought it was D. That's right, it's C. Okay, discretionary is C, yeah. Anyway, is that better, folks? I see a link about Kahoot, but I don't think it has anything to do with Kahoot. I think it's Twitch. Anyway, all right, let's go here. And I think there's another one. All right, what's the modern international method? All right, well, I guess I can't do anything about this 10-second delay. It used to be 20 seconds, and I raised it to 30, hoping that would compensate. Should I make it even longer? All right, it's common criteria. Anyway, is the answer to the question. Okay, and well, I'll carry on. I know the Kahoots help a lot to make the class less boring, so I'd like to make them good. Let me know if you think I should make them even longer. Playable as is. Yeah, I think that's one thing about it is it should be the same for all the students, so the competition is the same, and you only win by being really fast. But you know, it's too bad if it's annoying. So far I don't have any better way to do it, but I'm always open to suggestions. Yeah, well, before stopping the stream and restarting it made the lag go down. Anyway, we'll have to get used to these systems. Yeah, I think that is probably true. The delay might mean that you can never get 1,000 points, but it should be the same for all the other students. Anyway, let's talk about the secure system design. So one big issue is layering. This is applies to software and hardware. I remember back in the early days when computers were really new, like in the early 80s, you would have to buy a printer that matched your computer. But then they discovered you could layer things. You have operating systems, you have applications here, you have the kernel and device drivers here, and then hardware. And now you could make a printer, and the printer could work for various different kinds of computers because all you had to do was give it a device driver for the different computers. So only a small piece of software was necessary to connect to different operating systems. And so that's one concept of layering, and this applies to the electric plugs we have in the wall, and the network cables, and the radio frequency, Wi-Fi, and everything. It's all got these layers, so different devices made by different manufacturers will all work together because they each only cover a certain area of functionality, and then they have a standard interface to the next level. So another issue is abstraction. If you use a web browser, you just see things like pictures and videos and emails, but there's a whole bunch of detail going on behind the scenes with electrical signals and IP addresses and stuff, and you don't see any of that. That's called abstraction. You just see part of the story, the part that's interesting to you, and the rest of it is concealed from you. There are security domains in your computer system. The big one, the ones that are used in modern operating systems are only two: kernel mode and user mode. Kernel mode is the high privilege part of your system that has the ability to directly access the hardware. User mode is where you spend all your time. Everything you launch on your desktop from your start button is run with your privileges as a logged in user, and it does not have access to kernel mode. So if you want to print something from your program, you cannot directly connect to the printer. All you can do is make an API call to a Microsoft Windows kernel extension or a Mac kernel extension, where you ask the kernel to please print it for you. You can't actually directly touch the code that prints. You just ask the kernel to do it for you because you're in user mode, and user mode doesn't have any direct connection to the hardware, only through the kernel mode functions that are available to you, put there by the operating system designer. and the device maker, or the device driver. So the hardware in x86 CPUs has 4 rings of protection, but it only uses ring 0 and ring 3. The intermediate modes were used by old operating systems that are gone now. Turned out nobody cared about that, so we just use ring 0 and ring 3 for kernel mode and user mode. Now there's a new idea, though, in about the last 10 years called hardware-assisted virtualization, just for running virtual machines. And so these allow virtual machines to run in ring 0, so they don't have to slow down all the virtual machines by running in user mode, so all the virtual machines have to make another call back into the ring 0 mode. And therefore they have a special thing which some people call ring -1, to be even higher level, where this allows hardware-assisted virtualization, and it has different brand names like Intel VT and AMD V. And you probably know this because if you install VMware or I think VirtualBox on a modern laptop, you often have to go into the BIOS and activate these features to get it on. So an open system is where you publish the specifications, the circuit diagrams, and the code for your software. Everybody can see exactly how it works, and they could build their own. That's what IBM did. It turned out to be a pretty bad business decision because IBM was so slow that third parties would build better computers faster and cheaper and undersell them. Closed systems is what Macs did, where they don't even put numbers on the chips, they don't publish any documents, you have to guess how it works, and that turned out to be the way to make a pile of money. All right, that's where everything is proprietary and you can't see it. All right, now secure hardware architecture. The system unit is the main case of a computer, in the old kind of computer that had a big box that sat on the desk. That has the components. The main component in there is the motherboard. This has the processing unit, the RAM, firmware to run it, and to control things like the keyboard and such, and peripheral slots to plug in devices. So you have a bus. A bus is just a series of wires that on a circuit board that carry data from one component to another. So it carries data from the processing unit to the RAM and the hard disk and the keyboard and mouse and display. These are the communication channels between the components. And so you have in modern computers, you have the north bridge and the south bridge. The north bridge is really fast, where the CPU sends data to the video and the RAM, things that are really fast, and the south bridge is for things that are slow, like the keyboard, the USB, and the hard disk. So the CPU does all the operations on the machine. It does as close to what you might call of thinking. It does all the math in the arithmetic logic unit, and it has a control unit that fetches the instructions one by one from RAM and feeds them to the arithmetic logic unit for processing. So you fetch the instruction, you decode it, you execute it, and then you output the result. And that takes a clock cycle, although a lot of instructions take more than one clock cycle, like up to 6. M1 max equals no bridge. Yeah, I don't know. I don't think so. They must. Yeah, I'm not sure. Anyway, the M1 uses ARM, though. That's what I know about it. I don't know anything else. So interrupts have been around forever in computing. There are certain times when something happens that you should respond to right away, like the user presses the power button to turn the machine off, or they press a key on the keyboard. If that happens, the computer really ought to do something about that quickly. So it signals an interrupt, which means the CPU should stop whatever it's doing and go perform the interrupt to deal with this signal that comes in. All right, a task. Now, very early computers were single processing. I remember when I used MS-DOS type computers, and at that era, I would write a document, and then when I printed it, I would go get a cup of coffee, because while it's printing, you can't do anything else until it's done printing. It didn't have any multi-processing, but now it has multi-threading. The task is broken up into threads, and each thread can proceed independently. So if one thread of instructions is waiting for something slow, like user input, the other threads can continue. So part of the processing can continue without all waiting for the slowest thing to happen. So all modern operating systems are multitasking. You can launch several programs at the same time. Now there's only one processor, although now we do have multiple processors, but typically you can only do one thing at a time. And so what it does is it gives each one a few cycles, then it gives the next one a few cycles, and the next one a few cycles, and rotates among them so they all move forward, but only one is being processed at any given time. Now, symmetric processing uses an operating system to manage all the CPUs. Asymmetric multiprocessing can have a separate operating system image on each CPU. So you have a watchdog timer. This will notice if something has crashed and just restart the system. All right, and there's two types of processors. The Intel processors are CISC, Complex Instruction Set Computer with more than 10,000 machine language instructions. The alternative is ARM, that's Reduced Instruction Set computers where there's a smaller number of instructions, but they're designed to run faster. And currently, a lot of people are moving away from Intel onto ARM because it turns out ARM can actually get more done for less power, and your battery lasts longer in cell phones and such. And as you know, the Mac is now moving to ARM, so we will all get to see if it's really better or not. But most people say it will be better. I've seen people say Intel is going to go away and everything's going to move to ARM because the power savings is so important that even servers are going to move to ARM, but that hasn't happened yet. So you have direct and indirect addressing. If you do this instruction, add EAX 8, it takes 8 and adds it into the value in EAX. So if EAX had 1, EAX is a register on the CPU, it now has 9. But if I add EAX bracket 8, what that means is go to memory location 8 and take whatever data is there and add it to EAX. And here, add 8 to bracket EAX will add 8 to the memory location of EAX. So if EAX contains 12, I go to memory location 12 and add 8 there. So this is indirect addressing. All right. Memory protection is like the non-interference we talked about. One process should not affect another process, even though they're all running on the same hardware. That's what you would like. So you got to have process isolation. It's done logically. It's not done in hardware. It's done by using these techniques: virtual memory, encapsulation, and multiplexing. Multiplexing, each process gets a different slice of time, like I was just talking about. And the virtual memory we'll talk about more. Each process runs in a virtual memory space, which it only gets certain memory to use, and that memory is different than somebody else's memory to use. And object encapsulation keeps copies of local routines separate for each object so they don't interfere with each other. These are all just ways to lay programs in memory so they don't interfere with each other. When a processor starts, it is in real mode with a limited amount of memory and no process isolation. Any process can write anywhere in memory. Then later in boot up, it switches to protected mode, where there are memory segments and rules of what segments you're allowed to write to. The x64 processor does not use those old memory segments and segment registers, but it does protect processes from writing into other processes' memory. So virtual memory maps the processes and hardware memory. So each process has its own memory space, which does not have any way to refer to memory in some other process. And another thing called virtual memory, it's similar, is you can, if you only have 4 gigabytes of memory, you can launch more than 4 gigabytes worth of programs because it will just take blocks of memory and put them on the hard disk temporarily. So you can, it'll swap them back and forth there. That's called virtual memory. So if you try to open a program when the RAM has gone to hard disk, it will have a page fault as you try to load the contents from memory, and it says, this content is not here, I swapped it to the hard disk, and now you have to wait while it swaps it back from the hard disk. So that's called a page fault. If you get a lot of page faults, it slows down your machine, and the cure is to buy more RAM. Anyway, so the BIOS is the code in firmware. Is that what Docker uses? No, Docker uses something called overlay file system, where if you have an operating system like Ubuntu Linux, and you put a virtual machine that's, say, also Ubuntu Linux, then all it does is make a folder, and it doesn't bother to make a second copy of any files in the Docker container that are already equal on the host. So a clean, if you have a clean Linux install, and you make a Docker container of the same version of Linux, it has a size of essentially 0 at first, because it has a pointers that point to the files on the host and say use those files. Then if you install software in the container, it will save just the changes in the container. So the end result is it runs like a virtual machine, but it's perhaps 100 times smaller and faster. So you can run many more machines on the same hardware, but it is much less isolated from the host, and that they call overlay file system. It's all the rage now because it's so much cheaper, but it's not as safe. Anyway, a good question. So when a BIOS is little code on a chip on the motherboard, when you turn on the machine, it runs the program on BIOS, and what that program does is it probes the hardware to see what you got. Do I have a keyboard? Do I have a display device? Do I have a floppy? Do I have a hard disk? It hunts around, and if it finds something to boot from, it then boots from that, like a hard disk. That's what the BIOS does. Now you can have worm devices where you can write on them once and then read many times, but you can't write on them again. So like CD and DVDs, TDR and DVD-R. Now the Trusted Platform module was brought up to go with Windows Vista in order to meet military specifications so that Microsoft could sell hardware to the, yep, that's right, floppies, yeah. Maybe I shouldn't talk about floppies anymore, but I did. Anyway, all right, the point of this was to meet military specifications to sell these machines to the military for classified data. So it has a cryptographic coprocessor called the Trusted Platform module, and this contains a key in its internal memory that cannot be accessed by the CPU at all. No program running on the CPU can steal the key, and this is what you use for full disk encryption, like Microsoft BitLocker. The key is stored in this special chip, so it's almost impossible for it to be stolen from any software, and that makes it secure enough to encrypt the hard drive. The same thing's in your iPhone. There they call it a secure element. It's the same place, a special chip just to hold the cryptographic key that is separated from where the processor can reach so that no malware can steal the key. This turns out to be a very good system. It makes the machine much more secure, makes the whole disk encryption so secure that you can lose a laptop or have it stolen, and you don't have to have a data breach disclosure because it's encrypted with this system, and that means you can trust that nobody's going to get it. There are a few attacks under special circumstances, but in general, nobody can get in something encrypted with this system. Data execution prevention adds permission to memory. So you can have a memory segment that is marked non-executable, and code put in that memory section will not run. This prevents an entire class of attacks called buffer overflows and in general memory corruption vulnerabilities that we're doing in the exploit development class, and you'll see this made an entire generation of malware obsolete. So it's quite valuable. And along with it goes a very similar one, address-based layout randomization, where every time you restart a program, it randomly moves in memory to a different location. So you have to have your code compiled to prepare for this, but the result is an attacker, even if they can inject code, and even if they can execute it in that memory section, they can't find it because they don't know where the program is. And these two things together greatly improve the security of Windows Vista compared to XP. These are both software. However, NX requires that your motherboard support it, and all motherboards have supported it for like 15 years now. DEP is, I think, purely software. But they both came, in the world of Microsoft, they both came in at the same time. They came in with Windows Vista. And they did make it much more secure than Windows XP. Good. And now they're in everything. They're also in Linux, they're in the Mac. The only thing they're not in is the Raspberry Pi. I was horrified. If you take the exploit development class, we'll get there. The Raspberry Pi does not have these features, which is pretty shocking. At least the Raspberry Pi 3 doesn't. Maybe the 4 does. Anyway, let's look at the last cahoots. 3C is enough for one day, I think. Yep, right on the hour, just like it should be. All right. All right. Gonna move this over here to record where we left off. Looks like this is it. All right. All right, what CPU ring is user mode? Okay, ring 3. Good. All right, users can't handle the truth, so the computer lies to you. What's that? That's abstraction. It shows you only a symbolic representation of things, skipping the details. Sort of like when you have to explain a technical issue to management. All right, what's the communication channel between components? That's the bus. Good. All right. So I launch Word. What is that? That's a process. Good. All right. What's the cryptographic coprocessor? That's the Trusted Platform Module. It is named after, I think, something from the Orange Book, or maybe from the Navy. Anyway, from the Orange Book, I think. The official military term. All right. I know who that is. And that person looks like a real name. That's not a very real name, so they're not going to get their points unless they come out of the closet. All right. So, that's it for this. I'm going to stop the recording.